is the, so if you have single reinforced beam and you are not able to design it for the restriction of depth, what is the solution that you have seen till now?
Sir, over
So we can use doubly
I mean, double.
You make it as, you design it as a double reinforced beam. So similarly, this is another way for the same purpose, which is to restrict the depth of a beam. And this is the case where you actually have a slab above the beam. You always need to have a slab above the beam if you are going to use this consideration. Okay, so you consider that the slab and the beam are monolithically cast and they act integrally, meaning they act together. Okay, so something like this, for example, these are bridge girders. So you see several beams over here, and on top of these beams you have a slab. Okay, so for the purpose of design of these particular beams, what they will assume is they assume the shape to be that rectangular part of the beam, and above that there's a slab. No, so there's a slab between these two. I mean, from this end to this end. So if I take this beam, there's some slab on this side, there's some slab on this side. So along with that, they take the shape, and that shape will resemble a T. Okay, so these are also known as T beams. Okay, these are also known as T beams. And if you come to the end, it will resemble the shape of a L. So it is, they call that as L beams. So the common term for them is flanged RC beams because they have something known as a flange. We'll see what that flange is. Okay, the slab thickness, at least some width, both sides of the beam. Some width of the slab, both sides of the beam is considered to contribute to the resistance of the compressive forces on the top of the beam. Okay, compressive or tensile forces which are there on the top of the beam. So basically what it says is the resistance of the beam is composed of the rectangular portion of the beam plus some part of the slab which is above it. So together both of them you consider and say this is the moment that this flanged beam can resist. So this makes the beam to resemble a T shape if it's one of these interior beams, or if it's one of the exterior beams, then it will resemble a inverted L shape. So for example like this, so you have, this is the beam, then you have cast a slab above it. Okay, then instead of just taking up to this part, you say that the beam is composed of some part of this rectangle and some part of the slab above it. So how much part of the slab above it? So that is a question. The top part, which is composed of the slab, that is known as the flange. That's why it's known as a flanged RCC beam. And the one below, the rectangular vertical portion, that is called as the web of the beam. So these terms, flange and web, they will be used you will come across these terms very often, not only for T beams. When you go to steel design, you will have I sections, channel sections and things like this, steel sections. So there also you will frequently come across these terms, flange and web. Okay. So since the beam and slab are cast integrally, the flange width might have to be calculated, meaning that, for example, this much width of slab. So if the spacing is too much, you may not be able to take that the entire width you can consider. Okay, it will not be effective. So there are some code recommendations saying that if you have a very large flange, you may have to actually see how much of it can be used for this calculation. So there's a formula for that saying width of the flange is given by L0 by 6, which is the L0 means it's the length of the beam. Okay, BW is the width of the web and DF is the depth of this flange. Okay, the thickness of the slab rather. Okay, rather the thickness of the slab. So there are two cases that you can get. One is somebody may tell you there's a T beam having a flange width this much and this much of web height, flange thickness, web width and all those things somebody may give to you. If it is directly given to you, you can just use the width of the flange which is given. If rather than that you are given a question where somebody says there are beams and on top of the beams there's a slab of this much thickness cast, the slab meters in that direction, and they tell you to design the beam. Okay, so in that case nobody has specifically given to you saying that the width of the flange is this much. So then based on the slab thickness and other things, you will have to actually calculate what flange width you need to take. Anyway, so when you solve the problem,
Sir, can you repeat the significance of these symbols L0, BW, and DF?
Yeah, that's what I told you. L0 means it's the overall length of the beam. Okay. BW is the width of this web. You see this web, no? The width of this one. That is BW. Okay. And DF is the depth of the flange. DF is this depth. F means web. W means web. B is obviously breadth and D is obviously depth. So BF is the width of the flange which you can consider. It is not necessary that it will be this entire thing. Sometimes if this whole thing is too long, then it may be only till some part of it. Okay. So that's what this is. And for L beams, similarly, you have another formula for the BF given in the code. So how do we design these flange? How do we design this flange RCC beams? Okay, the first thing that we want to find is in a normal rectangular section, it is very easy for us to locate where is the neutral axis. Okay, so you have the formula. If it's a single reinforced beam, it's very easy. You just say 0.87 FIAST divided by 0.36 FCKB. You find out XU, you compare it with XU max, and then you say whether it is over reinforced or under reinforced. Okay, and then you do the analysis. And if you're doing a design, then you just use the MU limit formula and you provide the required depth. So for that it is easy. Here there is the peculiarity of this thing is your neutral axis will be somewhere depending on how much thick the flange is, how much deep the web is. Okay, so the ratio of the depth of the flange to the overall depth or to the neutral axis location, that actually decides how to design this particular type of beams. So we have three cases for that. One is if we have a very thick slab. If we have a very thick slab, then it is quite possible that the depth of this flange may be greater than the depth of your neutral axis. Okay, so this DF is so large that it is going below your neutral axis. Okay, so for example, like this, say this is my stress block, this is my neutral axis, and I see that the neutral axis is either just below the flange or even more below it. It doesn't matter. Now what assumption do we make for a concrete beam for the concrete portion which is below the neutral axis? Is it useful?
There is no concrete.
There's no contribution from the concrete below the neutral axis. So if this is the case, where the depth of the slab itself is, or the depth of the flange rather, if the depth of the flange is greater than the depth of the neutral axis, then it means whatever is there below the neutral axis, it does not matter to me. Meaning that this thin portion, the actual web portion also does not matter to me for locating the neutral axis. Okay, so in such a case, if the neutral axis lies not within, if the neutral axis lies within the flange depth, okay, so if it is, if the neutral axis is either, within this portion such that the depth of the flange is greater than neutral axis, then everything below that, it resists only tension and you can just design it as you design a rectangular beam. Why? Because neutral axis is either here or somewhere above it, and therefore it is as good as designing a rectangular beam for me. So you can use the same 0.36 FCK BX into D minus 0.416 XU, and you can calculate the moment. You can calculate whatever you want. Okay, you can do the design whatever. So this is the first case where you have quite a large DF, and you are able to design it as a rectangular beam itself, even though it is a flange beam. The second case is, now this neutral axis has come below the depth of the flange. Okay, this neutral axis, okay, it has now come beneath the flange. Okay, it has come beneath the flange. So when that happens, this flange portion, okay, it can either be there with, so if you look at the stress block, which is given for this, for any concrete beam, there are two parts to it. There's a parabolic part and there's a rectangular part. Okay, there is a rectangular part. So there are two cases. So one case is, if you see that this flange, it is located entirely within this rectangle. Can you see this? I have drawn two red lines just to indicate that. This red line indicates the bottom of this rectangle. This red line indicates the top of this rectangle, and I see that this flange is contained entirely within this rectangle. Are you able to see, kind of understand this?
Yes, sir.
Okay, so it is contained entirely within that rectangle. So that is one case. And one thing that is said is actually the centroid of this whole shape, parabola plus rectangle. The centroid of this whole shape is at, I mean not centroid. What to say is, I mean this is 0.42x, you know. So I mean this, I mean if you take the relative heights of this and this, it will come 3/7. Okay, if you can just, this is just geometry. So whenever I say that if my depth of the flange is lesser than 3/7 of XU, if my depth of the flange is lesser than 3/7 of XU, that means my flange is going to lie within this rectangle. Okay, it is going to lie within the rectangular portion of the stress block. So that is case number 2. If the flange depth is such that it lies entirely within the rectangle of the stress block, then you see that this rectangle, the entire stress is same. Okay, the stress in this within this rectangle is 0.446 FCK, which is the design compressive stress of concrete that we have already seen. So then the stress in the entire flange is 0.446 FCK, not just 0.446. I have missed out an FCK over here. Okay, and the lever arm, I mean not lever arm, the distance to that is defined as DF itself. I'll come to why I have used a term as YF. You will know in point number 3. So we use this depth of the flange itself for calculating the lever arm. Okay, so YF will be a bit confusing to you now, but when you look at point number 3, you'll know what is YF. And obviously, the third case is the depth of the flange is it is actually lesser than the neutral axis position, but it is greater than the rectangle position, such that some part of the flange is within the rectangle, some part of the flange is inside the parabola. Okay, so this is an intermediate depth of flange, which is not as deep as the neutral axis. At the same time, it is more deeper than the rectangle of the stress block. Okay, so what happens is some part of this rectangle will be having 0.446 FCK stress. Not rectangle, the flange. Okay, some part of the flange will have 0.446 FCK of stress. Some little bit part of the flange will have some other stress according to this parabola. So that is the most complicated case among all. So if flange depth is such that it lies between the neutral axis depth and 3/7 of the neutral axis, why this fraction I've asked? It's basically just if you go back to the derivation of 0.36 FCKB, you will, when you find out how that 0.36 comes, you will know what that 3/7 is. It's basically just the geometric ratio of those two locations. Okay, lies between neutral axis depth and 3/7 of the neutral axis depth. Then the stress block is partially in the parabola and partially in the rectangle. Then for convenience, because it's very, very difficult to actually find out what the actual neutral axis position would be in such a case. Okay, it's pretty difficult to find it out. So for convenience, based on a lot of studies, the code book and other things also propose that you can take YF as 0.15 times of XU plus 0.6 times of DF. Okay, so you need not worry about how this comes. It is given to you in the code book. It is based on studies. Why they have given some? This is empirical. Okay, this is empirical, so you have to maintain the units. I won't say empirical. It's empirical means units matter, but it's not exactly. You see that there are some constants over here, 0.15, 0.65. Okay, they are not based on some derivation or anything. Okay, these are actually based on approximations. Okay, these two constants. It's approximated because it's a difficult task to actually find out YF for any given particular beam, which is in this kind of a situation. XU greater than DF greater than 3/7 of XU. Okay, so for convenience, we have this, and we'll have to use this in finding the moment of resistance or whatever. So these are the three cases of which you have to do when you design a flanged RCC beam. First thing that you will have to check is which of these three cases is it. Okay, obviously when you're given a beam, you don't know what to do. First thing that you will always check is whether this is the case, the first one. Why? Because if you satisfy the first case, then it is very easy for me to do it, just like a rectangular beam. If that is not the case, then you come to case number 2, saying that the flange is entirely within the rectangle of the stress block. Then at least why we do this is because at least we directly assume YF is DF. Okay, and then we just proceed, not bothering about anything else. And then if we find that even that is also not the case, then we have to come here, we have to solve for XU, then from XU we have to find YF, and then find the moment. Okay, so saying it will not make you understand. So soon when you do the problem of designing a flanged beam, you will understand how this procedure works. So it will be it's a little bit bigger than designing a doubly reinforced beam or a singly reinforced beam. It's a little bit more confusing, but once you do 1 or 2 problems, I will do maximum 2. I don't have time to do more than that. So if somebody wants to understand, they have to actually. I have shared the Krishna Raju book, in the files. Krishna Raju Living State Design book.
Yes, sir.
Yeah, so you can actually you will have to probably go through that and probably try doing some designs yourself. More than what I do in the class. And anyway, these things I will cover for you. Now we'll cover. Yeah, so you see the formula, no? What I showed for T means effective flange width. Okay, so this is like this. If it's a part of a slab system, it's like this. If it's isolated, then mostly you will come across this formula only. You won't be using this too much. These things have been seen. Control of deflection has been seen. Detailing requirements have been seen. Percentage of reinforcement. By the way, when we did the beam design, there's one thing that I forgot to tell you. See, we calculated PT. PT is equal to 50 FCK by FI into 1 minus root of 1 minus 4.5. All the big formula, no? We have used that. But always what you should do is after calculating the reinforcement, make sure this check is satisfied. What is the check? AST should be greater than 0.85 BD by FY. I have not done that in the problem. I forgot to do it. Why I'm saying this is if you're calculating PT and you get a very, very small area of reinforcement, which is required. Then you have to just check whether that percentage, that reinforcement which you divide is at least this much. Okay, this is minimum tension reinforcement that is required to be provided. It's very easy, it's just nothing, just do 0.85 times the breadth into effective depth of the beam divided by Fy. You'll get some mm square. Just see whether that mm square is, whether the AST which you calculated is more than this 0.85 BD by Fy. It has to be more than this at least. So this check I forgot to do. It's easy, I don't think I need to go back and show you how to do it. It's just a check whether 0.85 BD by Fy is satisfied for whatever AST you calculate. So this is flange sections. So XU less than DF. In the code book also these are given. You can probably open the code book and look through these 2 equations. Okay. So there I told you 2 things. One is what is that? XU is less than DF or DF greater than XU. This is the rectangle section. It says moment of resistance may be calculated from the equation given in G11. If you open G11 and see, you will see the same rectangle beam formula. That is also stated over here. Then they give the 2 cases, df by d exceeding 0.2 and df by d, sorry, not exceeding 0.2 and exceeding 0.2. So this corresponds to the same 3 by 7 df by xu, that thing which I showed, no? It is the same thing. Only thing they have shown it in a different form. Okay, they have shown it in a different form for see, because we want to keep a balanced section, under reinforced section. So in such a case, you can actually just check df by d instead of checking df by xu, which is which was shown over the df greater than 3 by 7 xu, or df is between xu and 3 by 7 xu. Okay, so those 2 cases you have, no? So these two are just an equivalent of that. So approximately they have just related it in terms of df by d instead of df by xu. And when they do that, instead of 3 by 7, you have the number 0.2. So you can use either of this. You can either use you can either go by this consideration, or you can go by this consideration. Why I taught 3 by 7 xu and that particular approach is it is because when you look in terms of the stress block, and if I want to explain to you how this thing comes, that is the way to explain it, because you look at shapes and you understand how these things work. This thing df by d which is given to you, it is once again approximated. Okay, basically you will not get a meaning when you look at this criterion which is given to you. But of course, for the purpose of design, both of them work. You can use either of it. 6p16 usage has been taught. And now the other part of lecture is slabs. Okay. So what we are dealing with now is something known as a one-way slab. Okay. So there are two types of slabs. Basically, you should know what a slab is. A slab is the structural element which first of all takes the area load which is placed on it, and then it is from the slab that the loads go to the beams. Okay. So one of the problems when we solved for beam design, I told you that I had given you some floor area and told you there's a beam spaced this much apart, and then I gave you dead load and live load in terms of kilonewton per meter square. Do you remember the problem which I gave? Load was in kilonewton per meter square. Do you recollect that? Yeah.
Yes, sir.
Okay, so that is the meaning of actually giving a load in a kilonewton per meter square, meaning it is an area load or it's acting on an area. What is that area? It's the area of the slab or the slab panel which is given to you. So from that slab panel only, I told you, you take half the width on this side of the beam and half the width on this side of the beam, multiplied by that width, okay, given by this slab and this slab. Then you multiply it with the dead load and live load, you get kilonewton per meter on the beam. Okay, so what does this tell you? This tells you that load goes from the slab and then it goes to the beam. Okay, this is the action of any framed structure. Okay, framed, F-A-F-R-A-M-E-D, framed structure, meaning that you have slabs, then you have beams, you have columns, then you have your footing. Okay, so it is different from having something known as a load bearing structure where you have a slab, directly it sits on a wall, and from the wall you have the footing below it, or the column and footing below it. So those are two cases. Anyway, so coming back to this, you see that this any slab is bounded by the beams on which the slab will sit. So there are two ways of supporting slabs. One is you can support the slab on beams like shown over here. Okay, there's a beam here, there's a beam here, there's a beam here, there's a beam on the fourth side. Okay, another option is instead of giving beams and below that columns, there CD drive is there. CD drive is there in the phone. Yeah. So either you can have your slab sitting on beams, or sometimes in a load bearing type of structure, there will be no beam, there will just be a wall, and directly on top of the wall, the beam will sit. So not the beam, the slab will sit. Okay, so with the beam or without a beam, how is the slab supported? There are two cases. Beam supported slabs and wall supported slabs. Okay, so these are the two types of slabs. Now, whichever of these two type of slabs it is, there's another classification which is made saying that one way or two-way slab. So what is the meaning of this one-way and two-way slab? So you have to look at how the slab is going to deform or how the slab is going to bend. Okay. Now I have two cases. One is supported on all four sides. One is supported only on two sides. So this one, when I load it, I know that when I look at it from the front view, this is how the slab is going to bend. Okay, this is how the slab is going to bend, meaning whether I am at this part, whether I am at this part, whether I am at this part, wherever along this direction, wherever I am, if I cut a section, this is how the deformation of the slab will look. Okay, so whether you are at this end of the slab or whether you are at the middle of the slab or whether you are at the other end of the slab, the section if you cut and you look at the deflected shape, it will be identical. Okay, so this is one case. How about here? How will the deformation be in this kind of a slab? Will it be same everywhere, or where will the deflection be maximum in this slab?
Center, sir.
Center. Okay, it will be exactly same at the exactly highest at the center. How about if I go to this end? How about okay, from the center if I go, if I move a little bit, say from the center I'm going 1 meter in this direction. Okay, so there the deflection will be lesser. Then I go even further 1 meter more apart, it will be even lesser there. Okay, so we see. So here we have a shape which is curved, and the curvature is same everywhere as I move from this end to this end. Here I have maximum deflection here, so the curvature will be maximum at this point, and I'll have let's see how I can show it as maybe. So see, for example, I have a piece of paper here, and if I support it only on my two hands like this, okay. If I support it only on this end and this end, this is how there will be a deflection. That represents this. Okay. That represents this shape. Okay, where it's cylindrical. It's almost like a cylinder. This surface. This surface is like a cylinder. Another case is if I just okay, if I make it like this, where I'm sorry, I don't have good, I don't have an arrangement to support 4 sides. So I'll have a thing where in the middle I have a maximum deflection, towards the corners it will reduce to 0. So that is the similarity to this kind of a case. So depending on how the deflection is, we classify as one-way or two-way slab. One-way slab means the deflection is going to be along only one direction. Okay. Two-way slab means deflection will be varying along two directions. So which one of this is one way, which one of this is two-way?
The two beams having is a one-way slab.
Two-way, two what?
Two beams on either sides.
You mean this one? You mean this one?
Yes.
Okay. You're right. This is a one. This did you say one or two? One way or two way? What did you say?
One-way slab.
This is a one-way slab because the deflection is everywhere along the same one single direction. This is a two-way slab. Okay. So the easiest way of identifying one-way or two-way slab is see how many sides it's supported. If it's supported only on two sides, definitely it's going to be only a one-way slab. Okay. Now, in the case where it is supported on all four sides, it can be a one-way slab or it can be a two-way slab. Okay. So how you say is if the slab is really long, okay, long dimension by short dimension is greater than 2. If that is the case, then even if it is supported on four sides, it will be almost like a one-way slab, meaning that maybe in this portion the deflections may be different near the edges, but everywhere in between it will be almost same, the deflection. So from practical considerations, if the slab becomes very long, Ly by Lx greater than 2, then even if you support it on four sides, it will be almost behaving like a one-way slab. However, if the Ly by Lx is between 1 and 2, okay, then it is, if you support it on and you support it on four sides, then it becomes a two-way slab. Okay, so two-way slab design is I mean, it cannot be done now. First, you'll be saying one-way slab design because that is easier. Okay, why is it easier? Answer is given by this figure. What does this picture look like? Does it, when I just give you this, are you able to say whether that is a beam or whether it is a slab? I mean, if I give you just this, are you able to differentiate it as slab or beam? If I give you just this picture, the one on the bottom, just this one alone. Okay, you'll be able to tell me whether it's a slab or a beam just by looking at this.
No, sir.
Just looking at this, you have no idea whether it's a beam or a slab. Okay, you just see two supports, you see a rectangular section which is bending. How do you say whether it's a beam or a slab? Okay, unless somebody gives you that it's proceeding for some distance in the transverse direction. If that is not if that is not told to you, then you do not know whether this is a beam or a slab. Okay, so for a one-way slab, the design procedure is exactly the same design procedure as a beam, except that beam width, there you have taken 300 mm to 50 mm something. Okay, width of the beam. Here, one-way slabs are treated as beams of width 1 meter. Okay, taking the effective span as the shorter edge. Okay, which will obviously undergo the deflection. Okay, so if you are given a slab which is supported on 4 sides and the Ly by Lx it comes greater than 2, Ly by Lx comes greater than 2, then you will take this as the span of the beam. Okay, you'll take this here. You'll take, that's what I mean. You'll take 1000 mm as the width and this Lx as the span of the beam. Okay, so the provisions for 23.2 for beams apply to slabs also. That's why it's mentioned over here, because slabs spanning in one direction and continuous over supports shall be designed according to the provisions applicable to continuous beams. If it's not continuous, if it's simply supported, you will apply the same provisions as you do for simply supported beams. Okay, and the only thing is, if you usually when you are given dead load or live load in kilonewton per meter square, no issue. You will just find the load and you can design it. Sometimes in a slab you may be given a concentrated load. Okay, you may be given a concentrated load somewhere, like somewhere acting in the middle or something like this. So in such a case, it is not that it's uncommon, but still, even for the uncommon case, the code has to tell you what to do. So if that is the case, you will just have to use this table to calculate this effective width of the slab. You will not be using 1 meter in that case. So you have said no, beams of width 1 meter. That's how you consider a slab. That is if you have uniformly distributed load throughout the slab. If you do not have a uniformly distributed load throughout the slab, then instead of 1 meter, you'll have to calculate this, and you have to use this as the breadth of the beam, breadth of the slab rather. Okay, so what is this? All these details are given here. I will not waste time on this. You can just go to the code book later and see what this means. And one thing you have to remember is, when you have beams, what you do, you find out the ultimate moment, kilonewton per meter. Then you find out load. In generally for a beam, a load will be given to you in kilonewton per meter. Moment will be given to you in kilonewton meter. Percentage of reinforcement or the area of reinforcement will be given to you in millimeter square. Okay, so this is how these things are given to you. But for slab, what do? You are considering a slab as beams of unit width. Okay, one-way slabs are designed as beams of unit width. So what do you think will be the units for these things? Load, moment, and area of stream. What do you think will be the units for them then? So you have something, and you know what to do for beams, and then you're saying a slab is nothing but one-way slab is nothing but we design it just as a beam of unit width. So what change do you think happened to the dimensions of the units of these things? Load, moment, and area of stream. For beams, it is kilonewton per meter, kilonewton meter, and millimeter square. How does it change for slabs, one-way slabs then, or any slab in fact, not just one-way slabs?
So 1 meter we can take as 1000 mm, right?
Yeah, that is fine, but no, that's not the answer. The clue is in unit width or per width. When I make all these dimensions to per unit width, how does the unit change? Clue is in per unit width. Okay, kilonewton per meter per unit meter. How does that? What is the new? What is the new unit then? If kilonewton per meter is written per meter.
Per meter square.
So load becomes kilonewton per meter square. How will what will moment become?
It will become kilonewton.
Kilonewton, but you should not write it as kilonewton. You should write kilonewton meter per meter. Okay, if you write it as kilonewton, the meaning becomes wrong. Okay, and similarly reinforcement also you will say millimeter square per meter. Okay, meaning that if you have 4 meters slab width, you will find out say 800 mm square. No, 800 is too much. Maybe 300 mm square per meter. Then you'll have to give 300 mm square in this first 1 meter, then 300 mm square in the second 1 meter, like that. So 300 into 4, 1200 mm square you'll have to provide. But nobody will say provide 1200 mm square for the slab. They'll say give this much mm square per meter. Okay, so everything becomes per meter when you design a one-way slab. Okay, so similar to how if you remember this for beams, continuous beams we had designed. I did not do. So we gave this mount question saying that if you have a continuous beam and you want to design it, how to actually design. So one problem like this we will do for slabs, and the same thing only will be applicable even to beams also. So that thing I'll tell you later. So mount questions for continuous slabs or continuous beams, whatever they are. These are easy questions. You can refer the IS 456 table which I showed you some days back, or some weeks back, so that you know what is the moment you have to design for in a continuous system. Okay. And this is how the reinforcements will look. Near the edge, you see that the reinforcement is coming at the bottom. This is a slab, by the way. So there is reinforcement coming, then going up, then so you see that near the support, the reinforcement has been bent up and then taken to the top. So anyone knows why this reinforcement is going to the top here near the edge? The clue is here. So this is the edge of the beam, and the reinforcement I'm saying is taken to the top at this location. The clue is here.
This is the hogging moment.
It's a hogging moment at that location. So your tension goes to the top rather than at the bottom. Okay, so therefore you lift up, bend the beam up and take it. So this is done even for beams also. If you have a continuous beam, the AST which you provide, you have to calculate it at the span, you have to calculate it at the support, and then separately at the support you'll have to give AST for the hogging moment. You have to calculate it and do it. If time permits, I'll do one such problem. Otherwise, no. Let's see. So this is one thing that you have to remember. And other thing is, obviously for a slab, you'll have to give reinforcement in 2 directions. If it is a one-way slab, you will calculate AST along the main direction which you have found. And for the other direction, you have to use that 0.85 BD by FY. Okay, no, that is for beams. You will have to use 0.4% of BD. That's the minimum reinforcement to give in a slab. Okay, point 1. I will come back to that. Okay, so there's a minimum reinforcement percentage which you have to maintain in a slab. So you will give that along the other direction. So one-way slab, you'll find out AST, give it along the main direction. Okay, and in the other direction, you will find the minimum reinforcement which is to be provided, and you will give it. So you should not leave a slab with just giving reinforcement in one direction. You have to give it in 2 directions. Okay, so what is the time? Okay. So here I don't want to start now. Maybe something in the code book I can show you. So tomorrow and day after tomorrow, we'll do some problems on slabs. Just a minute. If it's something, always go to the code book and try to find out where those things are present. And that becomes important. Okay, since I have a few minutes, I'll just show you from IS 456 where everything which I showed you was present. Okay, so T beams and L beams, you can see you're able to see my IS 456, right?
Yes, sir.
Yeah, so you just go through these things, T beams and L beams. A slab which is assumed to act as a compression branch of a T beam or L beam shall satisfy the following. They should be cast integrally and all these things. You can just read about these things. Similarly, effective with the flange. So those formulas which I showed you are given over here for T beams, for L beams. And if they are isolated, then this formula just changes a bit slightly. Okay, control of deflection, these things I showed you already. Modification factor for them. Then we come to solid slabs. This is what is there for slabs. The provisions of 23.2 apply for slabs and beams also. And the first note is for two-way slabs that I have not come to yet. So you see the control of deflection equation now here. A cantilever means 7, simply supported means 20, continuous means 26. So these values are not the same for slabs. For slabs, they are a bit different. So that is given over here. The ratio becomes 35 and 40. For slabs, the L by D criterion is much more lenient. Okay, it is much more lenient. And this is for, I suppose this is for mild, so it says mild steel reinforcement. Okay, meaning Fy equals 250. Okay, for such a case, this is 35 and 40. If you use Fe415, it's 35 into 0.8 or 40 into 0.8. Okay, just given below over here. Fe500, nothing is given. No information is given to us on what we should multiply by. If I find out, I'll tell you. Otherwise, we just use 0.8 if you want. But usually, people will not that much worry about deflection in slabs. Okay, usually it is assumed that it will be met. But anyway, it's always good to check it. So slab spanning in one direction continuous over the support shall be designed according to the provisions applicable to continuous beams. Okay, so if it's continuous beams, if it's simply supported beam, just like simply supported beam. And this is the thing for concentrated load, you cannot use 1 meter effective width. You have to use this formula that I showed you already. And this K, X, L, E, F, all these things are listed over here. K is a constant having the values given in the table, depending on the ratio of the width of the slab to the effective span. So you find out the width of the slab by effective span, you have some ratio. Then you can pick out what is K for simply supported and continuous slabs. X is the distance of the centroid of the concentrated load from the nearest support. So for example, if you have a load at the center of the slab, the distance from the boundary to the center of that is X. Okay, width of the contact area of the concentrated load near the support measured parallel to support. So this is if you have a perfect concentrated load, you don't have anything for A, it is 0 if it's perfectly concentrated. Sometimes instead of having a perfect concentrated load, you'll have a small patch of load. So if you have a small patch of load, the width of that patch is A. So this I'm just telling you so that we will not be doing these problems on concentrated load and all. The reason that I'm telling you this now is in case somebody in the future takes advanced reinforced concrete design elective, for you it's an elective, for your seniors it was a core course. Okay, So if anybody takes that course, when they do bridge design, so the wheel of a heavy vehicle acting on the slab of a bridge, what type of a load is it? Is it uniformly distributed or is it concentrated?
The concentrated.
It's a concentrated load, except that it's not perfectly one point. The wheel of the heavy vehicle will be a little bit flat at the bottom. So there's some small width over which it acts. So that is known as a patch. So somebody wants to design such a slab, they'll have to know this. Okay. So that's why these things are given. Two directions of right angles. There is a two-way slab. This is given separately in the annex. It's not mentioned over here. Okay, so these things will be given to you when you do two-way slabs. It doesn't need to be done now. Relevant stresses, after reinforcement, all these things were covered to you. Yes, it is reinforcement. Beams. Yeah, so slabs minimum reinforcement, the detail is given here. This is what I was searching for. For mile steel reinforcement, the minimum reinforcement in slab should be 0.15% of the total cross-sectional area, meaning B into capital D, not B into small d, B into capital D. So if you use FE 415 or FE 500, it is 0.12%. FE 250 means it is 0.15% of the total area, not B into small d. And there's a restriction on the size of the bar also that you can use. You can use reinforcing bars that are maximum of 1/8 of the total thickness of the slab. This reason is being because usually slab thickness will be like, for a normal construction building, slab thickness will be like 120 mm or 130 mm. Okay, not like beam 3 and 400, 500 and all. It will be only 130 mm slab thickness. So there and all, if you give 32 mm bar and all, it is too much. 20 mm bar, 25 mm bar. So there's a restriction placed on the diameter of the bar that you can use. So these are some things that I just probably wanted to show you in the code book. And of course, I can show you. So, so all these formulas you can see over here. XU by D, mu limit. Okay. So everything that you need is given over here. Similarly, if you have W reinforcement, this is also shown to you. So this is shown. Okay. And for flange sections, how do you find mu? Answers over here. Okay. So if it is depending on the dF by D value, you'll just be using this. Okay. So if it's the case where dF and XU are between 3/7 by the intermediate range, so then you'll have to find out this YF, which I told you, which is given by this formula. Okay, this is also shown over here, and this is how we find the reinforcement. Okay. So here you can see that dF by XU is 0.43 or not 0.43. 0.43 is nothing but 0.43 is 4/7, or 3/7 I said. The remaining part is 4/7. That's what is written over here. So it's the same equations as shown. So even if you don't remember these big equations, open the code. Don't say that you don't know how to write it. You have the code book. Even when somebody is sitting in the hall and writing the exam, many times students will forget the equation. They'll not write anything without knowing that they are allowed to use the code book in the exam, and the code book itself is giving them all these equations to use. Okay, so please be aware of these things. Okay, so with this I'll stop, and so we'll meet again tomorrow. It's late. I'll end the meeting. Okay, bye. See you tomorrow, 10:30.